Friends, today we are going to look after that how Einstein derived his field equations of gravity or gravitation. We know general theory of relativity is the one of the two greatest theory in the whole branch of science. This is the theory which is very important along with quantum mechanics to describe the whole secrets of the universe from, from large scale to small scale or a small scale to large scale. Now we have to look after that how Einstein was deriving his field equations. That was the fundamental law of his theory of general relativity. His theory of general relativity has the fundamental equation, most fundamental equation, which is Einstein's equation, which is Einstein's field equation. So now we are going to look after how Einstein derived it, how Einstein came up with his field equations, what was the process that led him to discover it. Now, first point is that it was in 1907 that Einstein gained the principle of equivalence with the greatest inspiration of his life. So it was in 1907 that Einstein gained that the equivalence principle. That means the gravity is just an acceleration. Gravity equals acceleration. So this was the greatest inspiration of his life. In his own words, it was the happiest thought of his life. But at this time, he did not immediately devote himself to general relativity. Okay. Second, in 1908 and 1909, he immersed himself in the study of quantum of light. So, in 1908 and 1909, he was not working in this uh, field. So, he was working in the other field, light quantum. Now, it was around June 1911 when he was a professor at Prague University that he imagined a curved space and felt the need of a new geometry to express it through a thought experiment in which clock runs slowly and light bends in a gravitational field. And this thought experiment was rotating disk experiment, rotating disk thought experiment. So this was the most wonderful, one of the most wonderful experiments, thought experiments ever conducted by any physicist in his brain, in their brain. So then in July 1911, returning to his alma mater as a professor of Swiss Federal Institute of Technology in Zurich, Einstein embarked on a full scale study of deriving the field equations of gravitation to explain the role of gravity. So it was in July 1911 that he was fully immersed to derive the field equation of gravitation. Um it was according to his expression to discover God's thoughts. Then Einstein encountered a huge obstacle. It was a geometry that expresses a curved space, and this was Riemannian geometry. Everyone, he found mathematical tools. He conceived that Riemannian geometry was a mathematical tool for describing the secrets and also the structure of the universe. So it was Riemannian geometry, that is the differential geometry, that was discovered by George Bernhard Riemann, who was the greatest, one of the greatest German mathematicians ever lived in the history of the humankind. So it was Riemannian geometry, which is only capable geometry to describe the structure of the universe. Okay. Now, besides, he also got the principle of general covariance corresponding to the principle of relativity. Now that Einstein has the two pillars of equivalence principle and the general covariance principle plus the mathematical tools of that remains is to construct an equation. So Einstein at last had developed all the people pillars for the you know uh, his theory of general relativity. He discovered equivalence principle. He discovered general covariance principle plus mathematical tools he practiced. So after all, he had to construct an equation that uh, that was God's thought, according to him. Now, even God is also governed by this equation, you can say, because according to Einstein, as Einstein was the believer of Spinoza's idea, we all know that Spinoza was the one of the greatest enlightenment thinker who thought of that God is nothing but the laws of nature that governs the whole universe, whole cosmos, is the real God. So this was the definition of God according to Spinoza, and Einstein was the uh, man who believed on Spinoza as God. So according to him, it was the God's thought to which he was going to discover. Now, the path to the field equation was very tough. Okay, even also for Einstein. Yes, Einstein was a genius, but the path to the field equation was very tough, even for a genius. Okay, but Einstein followed the path very bravely. There were many difficulties came into the path, but he crossed all anyway. Yes, there were many problems: Max principle, general covariance, mathematical difficulties to set up the equation. There were many problems he had faced in his path, and but he crossed bravely. Yes. Now, for example, there was a problem unsolved in physics, that there is an interpretation that Einstein believed that the general covariance principle violated Mach's principle, but is not, but it is not sure if that is true or not. Yes, Mach's principle says somewhat about gravitation, aftermath of Gauss's law of gravity and Newton's law of gravity. So this was inconsistency that was not solved in physics at the time. So Einstein was also crossing this um problem. Now, anyway, researching 3 years, nearly 3 years, he realized his mistake and returned to the rigid path in 1915. Otherwise, if this didn't exist, uh, then he ultimately derived his field equation in 1912, I think. Yes. Now, in 25th of November of 1915, what is the date? This is the most important and crucial date in the history of physics. In 25th of November 1915, delivering fourth lecture in a physical mathematical session at Prussian Academy of Sciences, Berlin. He completed he completed his field equation for his theory of general relativity, making the historical event in physics history, the birth of greatest and most splendid achievement of human thought in our lifetime. Okay, he developed his equation into 10 second order quasi-linear, a type of nonlinear partial differential equations, PDEs, and tensor equation. It was also a tensor equation. He completed it with the greatest concentration of his life. That's why he considered this theory, general theory of relativity, to be the greatest achievement in his whole entire career. So this was the greatest, yes, achievement, even not for Einstein in his life, but for mankind. Even Interstellar movie, all the scenes that are very um, uh, exciting and amazing, that were shocking for many viewers. All this follows the principles and the equations of general theory of relativity. Yes, this was the fact, the scientific fact. And Interstellar movie was assisted by the great one of the greatest living theoretical physicist of our time, Kip Thorne, American theoretical physicist, who worked for LIGO detector and was awarded 2017 Nobel Prize in Physics. And this was the greatest achievement, one of the greatest achievement for all um, time for mankind. It was first time that mankind ever detected gravitational waves. I will make another video on gravitational waves, because these are the waves very different to any other waves, even you heard of any of. Now, where are we? Us. Now, he completed it with the greatest concentration of his life. After all, he applied it to the shift of the Mercury's perihelion and deflection of starlight by sun's gravity, and it gave a more accurate value than Newton's theory of gravity. Yes, so Newton's theory of gravity predicted somewhat wrong results, non-accurate results, and it was Einstein's theory which was very helpful here. For the It was very century problem, Mercury's perihelion motion. Yes, it was very century. Even Einstein's theory of general relativity, which he developed, was also using this experimental and observational thing. He used this observation, Mercury's perihelion motion, and by using this, he also used this observation to develop his field equation. Yes, deflection of starlight by sun's gravity. He also used this thought experiment, which is also true, and it is also called the gravitational lensing effect, and it gave a more accurate value than Newton's theory. Yes. Now, historically, we are going to see how historically Einstein modified his field equations and came up with the great field equation at last for gravitation. Now, Einstein modified his equation in 1913. This Christoffel symbol gamma mu nu equals k kappa. Kappa, it is known as small k for Greek letters. Kappa, it is called T mu nu. Okay. So here is about the geometry of space-time, curvature of space-time, and here is T mu nu. Here is all about the stress energy of matter, stress energy tensor of matter. Yes, this is a tensor equation. These all are. Now, on 4th of November, he was giving 4 lectures in 4 weeks per week, a lecture in per week in the month of November in 1915. So it was a time when he was going to complete his theory of general relativity, and it was very, very historical event. Okay, on 4th of November, R mu nu equals minus kappa T mu nu. What is the meaning? R mu nu is the Ricci curvature tensor. Okay. No, no, no. It is the part of Ricci curvature tensor. He used G mu as a Ricci curvature tensor. Yes. So historically, if you go to see what was Ricci curvature tensor according to Einstein, which he used in his field equation at that time in 1915, so it was G mu nu. G mu nu equals R mu nu plus S mu nu, I think. So R mu nu is the part of G mu nu. Now, R mu nu equals minus kappa T mu nu. We know T mu nu is what? It is stress energy tensor. On 11th of November 1915, after a week, G mu nu equals minus K T mu nu. He realized the modifications, all these modifications per week, and after all these things, after all these concentrations, he arrived after uh, just after 2 weeks. Here is written, he arrived at the final field equation on 25th of November 1915. G mu nu equals minus kappa times under bracket T mu nu minus 1 half small g mu nu T, bracket closed. So this was the final field equation in his own historically, precisely in his own words. Yes, in his own form of 1915. Yes, in 1917, but in 1917 he also added a term, cosmological constant lambda, uh, in his field equation to predict our universe is static, not dynamic. So what was the point, guys? This equation which he published in 1915, it was very, very powerful equation, and it also predicted what it also predicted that Einstein cannot even imagine in his life that universe is also dynamic. Universe is dynamic. Universe is not static. If universe is dynamic means that it is expanding or contracting, but not static. So this was the inconsistency to the philosophy at the time. So Einstein was somewhat believing in philosophy at the time, so that's why he added it in his field equation. So you can see here that Einstein's field equation for gravitation was much smarter than Albert Einstein. Yes, that is reality. Einstein not believed in black holes, wormholes. All these things are predicted by his field equations. All these things, singularity, and birth of the universe, and all these things were predicted by Albert Einstein's this most genius equation. Now, here in 1917, he did in 1917, G mu nu equals minus, sorry, equals not here, G mu nu minus lambda small g mu nu equals minus kappa times under bracket T mu nu minus 1 half small g mu nu T, bracket closed. So this was the equation along with cosmological constant which he, you know, added to avoid inconsistency. Now note, but the simplest version of his field equation was published in his theories treatise. That means there were many treatises written on his theory. There are many books, textbooks, like Stephen Hawking's large scale structure, and many more. Um, but this treatise, this textbook, gravitation, by Misner, Thorne, and Wheeler. So you can see Charles W. Misner, Kip Thorne, and John Archibald Wheeler. Here are the three greatest physicists of the century. One of the greatest physicists of the whole 20th century. Three written a single book, 1300 pages book, Gravitation, and it was a classic book. You have to know that it is a classic book, Gravitation. uh, all the mysteries, secrets, mathematically written in the book of Gravitation about general theory of relativity, from A to Z, everything mentioned in this book. Okay, now you can see Thorne, Kip Thorne, which I was telling you. Kip Thorne, the winner of 2017 Nobel Prize, developer, one of the developer of LIGO detector, theoretical developer. He also wrote this book. And Wheeler, Archibald Wheeler, John Wheeler was great scientist who discovered the absorption theory with Richard Feynman, and the process of nuclear fission, all this. In 1973, the simplest version of the Einstein field equation, of gravitation, that mentioned in this treatise, Gravitation, and it was of form G equals 8 pi t. And what was the letters denoted here? Where G is Einstein tensor. Einstein tensor is that um, r mu nu minus 1 half small g mu nu r, where r mu nu is a Ricci curvature tensor, and r is Ricci curvature scalar, and g mu nu is metric tensor or fundamental tensor according to Einstein. So this was G, which is very concisely, you can think of that, this concise letter expresses all of Riemannian geometry in the left hand side of the equation. The whole mathematics, whole Riemannian geometry on the left hand side, and T, stress energy tensor, the momentum, mass, energy, stress, pressure, density, all these physics terms, matter, about matter, is on left hand side. So this was the greatness of this equation, G equals 8 pi t. But main point is here is that the main point here is that there is a mistake. You all know, you can know that G should be of bold, and T also. T and G should be bold. Why? Because it is a tensor. Tensor is always bold. Otherwise, it should be denoted to be uh, also with mu nu. R mu nu, just like, let's say, it is a tensor, because we have to mention the coordinates. Here are mu nu. Mu nu are coordinates. But if we are not mentioning the coordinates, then we have to write it in which form? Boldface, uppercase, boldface letter. Now here G mu nu, we can write G mu nu as the boldface and uppercase G, and uppercase and boldface T. Okay, so this is Einstein's field equation in very simple form. I mean, this version is my favorite. Even Einstein's field equation is my favorite equation, and this version is more favorite for me. Now, but 13 years later, when in 1930, Edwin Hubble discovered the expansion of universe, and so no longer was the cosmological constant necessary. Einstein abandoned it, calling the biggest blunder of his life. So there was the experimental discovery, or we can more precisely, more accurately, we can say observational discovery by Edwin Hubble, Mount Wilson Laboratory Observatory. He discovered that the universe is expanding. He discovered the Andromeda galaxy is gone far according to some distance method, astronomical distance method. He calculated all these things, and he concluded that the universe is not static, it is expanding. And that's for Einstein, that he realized that the cosmological constant was not so necessary in his field equation. It was making wrong his equations prediction. So that's why Einstein abandoned it and calling the biggest blunder of his life, the biggest mistake. Now, and returning to his original equation of gravitation in 1930, he wrote this expression. Okay, he wrote this, but famously he delivered a lecture, The Meaning of Relativity. The lecture name, Meaning of Relativity, of four lectures, a set of four lectures at New York University while a visit in 1922. Okay, and it was also published as a book, The Meaning of Relativity by Albert Einstein. And in this book, he wrote this version of relativity equation of gravitation: r mu nu minus 1 half small g mu r equals kappa t mu nu. Now here is something written as a quote: when forced to summarize the general theory of relativity in one sentence, time and space and gravitation have no separate existence from matter. Albert Einstein said these words when he was asked, in an I think autograph or interview. He was asked what is your new theory of relativity, general relativity, describe it in one sentence. So he replied this quote. That's why it is very, very powerful and important. And by John Wheeler, I had described you. uh, his very, very, very poetic and charismatic quote about general relativity is that, describing the whole theory of general relativity in 12 words. You can see: space-time tells matter how to move, matter tells space-time how to curve. Space-time tells matter how to move, matter tells space-time how to curve. So this was Einstein's theory of general in very, very poetic sentence. Whole theory of general relativity can be described in, yes, you can say. So this was all about Einstein's theory of general relativity. It was very beautiful theory. It is very, very, very beautiful theory ever created, you can see. So I hope you enjoy this, and thank you everyone.